Hello everyone, this is me and Ashmitha from Meta. Today we want to share our recent experiences in improving network communication, debuggability, and observability at large-scale training. Let's first take a look at the network operation where we are in large-scale training. Typical large-scale language model training often suffer from thousands times of collective communication per iteration. The exposed communication cost may occupy more than 13% of the total training time. During that time, the GPUs are completely idle. Moreover, the communication cost further increases with system scale. We need to pay a lot of attention to keep the network speed to full speed to reduce the exposed communication cost as much as we can. From the other aspect, the healthy status of the network also playing a very important role in training efficiency. If there's any network fault happen, it causes job crash and has to be checkpointed, restarted. The checkpointing and the restarting process may take 10 to 30 minutes in full system scale, which means all GPUs of the system has to be idle during that time. Obviously, it's very essential for us to ensure the network functionality is reliable and the performance is always at the full speed. Meta has operating parallel training on HPC-style supercomputing systems starting around 2020. The system typically consists of GPUs connected with a RoCE network. Most of our production workloads during the past years are ads models. They are running around 100 GPU scale. We have built an enriched operational routine based on these 100 GPU scale workloads. For example, we scan every machine's healthy status before job starts and collect log from each machine. When any failure happens, we allow operational engineer to process and change based on those logs. This worked well of our traditional workloads. However, since last year, we started host a brand new set of large language model. Those workloads scale from several hundred GPUs all the way to tens of thousands GPU scale. And the existing operational routine no longer suitable for that large-scale training workload. Specifically, during the January, we observed there are a number of new operational challenges we are surfacing in large-scale training. First of all, the communication it happens in a very complex software-hardware stack, and the large language model often has multiple stacks, which we will go detail in the later section. And secondly, because of the scale of the workload, the traditional log-based post-failure analysis is very inefficient because we have to digest a large amount of data. Many of them are noisy. And also because of the scale of the network system, we often hit unexpected network congestion, which happens much more frequently when we run at a small scale. And when we think about how operational engineer or model developer try and debug issues, we often need to have a reasonable understanding of the model performance and the network healthy status correlation. However, because of the complex software stack, as we mentioned at the beginning, this routine becomes very challenging and impractical. Lastly, but most importantly, if we do not have an efficient troubleshooting routine, the cost is going to be more and more expensive at a large scale, because every time when we restart the training, it's going to take us 10 to 30 minutes. That's a very expensive cost. So next, I will hand it over to my partner Ashmitha to go deeper into the performance observability aspect.
Thanks, Min. So before we dig into the observability stack that we built, let's look at the anatomy of a large job performance regression. So when a model developer reports a training regression, one of the questions that these network engineers get asked is the slow communication the reason for the slowdown? If network indeed is the root cause for this performance regression, is it because one of the endpoints is slow? For example, is it a slow PCI connection problem, or is the network medium itself slow because of bad routing or packet drops? So why is this a hard question? One reason is complexity of the systems. The training stack involves multiple hardware components and software layers of abstraction, which have tight dependencies on each other. This makes it challenging to know if either compute or the network is the root cause for the performance problems. Secondly, our existing monitoring systems don't give us a model-aware network performance signal. We have metrics like timeouts and packet drops, which clearly tell us that there's a problem in the network. But there are other secondary metrics like ECNs, which do not always indicate a problem. But there are certain scenarios when it results in significant performance degradations. So just looking at standalone metrics, we cannot localize the problem to specific ranks in a job or even know which exact communication stage has slowed down. Third reason is the bad hardware detection. There can be hardware-software issues in our infrastructure that can remain undetected, which can lead to very long training hours. Failure to diagnose such problems and have proper signaling can lead to training process continuing under suboptimal conditions, which leads to poor model performance. Lastly, the scale of the infrastructures. The hardware metrics can generate too huge volume when operating under thousands of GPUs, which makes it impractical for manual triaging. So what's the best layer to add this instrumentation? We know the training stack is complex and has multiple layers of abstraction. So when we think about the right layer to build this observability, collective communication library stands out. This is because the collective library was designed to abstract the network away from the ML training framework. So now that we know what to build and where to build, let's talk about the solution. So our solution is to have a generic real-time tracing integrated in Meta's own custom communication library called NickleX. With our custom build library, we can now translate the training communication request down to the lowest level transport operations. This has allowed us to build more collective and model-aware network performance tracing. It also provides us the flexibility to add tracing which is more tailored to our needs. Starting from the collective down to the transport, we can choose what events to track, how to format the data, and store the logs. By analyzing the trace data, we can now identify areas where the training process is slow or inefficient and take suitable actions on it. Since it's custom built, it also makes it easy to integrate with other tools and libraries with our existing infrastructure. So now that we have talked about our design, let's look at some of the applications of the workflow we built. Before we do that, what is slow rank? And how did we identify this slow rank problem before? So in this example you're observing, we have 4 servers with 8 GPUs communicating with each other. So when one of the NICs slowed down due to a PCI issue, we were able to detect this problem before in the receive direction using PFC counters. However, when the senders slow down, we don't have any counters to signal this problem, which means we don't even know if the senders or the GPUs are pushing the network hard enough to begin with. We just spent the last few minutes understanding the performance profiler we built to understand if collective is slow due to an endpoint issue or a network. But how do we know if a slow collective is actually resulting in a slow model performance? So in this showcase, we show how we can combine 3 visualizations that we built in order to complete the debug workflow. Firstly, the model performance timeline. It can tell us if there is any regression in how fast the model is consuming the tokens to train. Secondly, we can use a detailed breakdown of the various parallelisms involved in the communication. This can tell us how much is the exposed communication time, indicating the most sensitive communications when it comes to model performance. Third part is something that we already visited, which is the performance profiler bandwidth measurements that can tell us if there are slow ranks or slow network. So we talked about using this workflow to understand performance regressions, but we can use this very similar workflow to also identify performance optimization opportunities. For example, if we can identify FSDP parallelism is the most exposed communication pattern, then we can spend more time tuning this collective as opposed to tuning other collectives. Okay, now I'm going to hand it over to Min, who's going to talk about how we debug failures in our training jobs.
Thank you, Ashmitha, for the amazing introduction of our performance regression debugging. Now let's take into a few minutes to study how we have doing with our failure debugging. The typical network failure debugging flow involves triaging and root causing analysis based on observed job failure, commonly some process stuck during the training. The cause can be often invalid user program, software bug, or a hardware fault. The classical debugging routine based on post-failure analysis, such as relying on per process log, such is not scalable when we debug with large amount of training processes. Moreover, when the software-hardware stack becomes more and more complex, as Ashmitha also demonstrated in the performance regression debugging, the traditional manual understanding of those logs from various stack components becomes completely impractical for our operational engineers. However, we need to understand that it's especially important for us to efficiently, quickly root the cause and fix a network failure, because the cost to shut down and restart a training process is very expensive. For example, our previous Llama 3 training may occupy more than 20 minutes for tens of thousands GPU just to start and prepare for the first iteration of the training. All of those motivated us to look back and reevaluate our debugging routine. We applied a semi-automatic failure localization during our large-scale training bring-up. So these slides, we want to go over this solution and see how it looks. It works. We built the semi-online failure localization system that tightly integrated into PyTorch Nico training stack. It's a very similar approach as we did for the performance observability aspect. Specifically, we trace all the collective communication on each process in our communication runtime library Nico, where we know the model correlation as well as all the internal network operations at real time. When any stuckness or network timeout happens, we run an expert knowledge-guided script to aggregate the per-rank tracing data and find the root causing pair of the training processes. Any invalid user program or hardware fault can be identified via different pattern and signals. Thus, we can process the root cause the failure and localize the failing hardware if it exists, and we can quickly process and fix it. Now let's take two examples to go through the solution and show how we resolve the different type of failures. The first example I want to share is a large-scale job that stuck and hit system timeout due to a network hardware fault. The graph showing here is a three-dimensional parallel training in our Llama 3 training job. You can see there are three ongoing communication happening. The tensor parallel altogether, the pipeline parallel send and receive, and also the FSTP altogether. All of three of them are stuck during the training at one point. And we don't know why that caused and which collective is the root cause. The challenge to use pre-existing approach here is that we need to post multi-process Nico logs and manually correlate the hardware matrices from tens of thousands ranks here, and that would take hours for us to process the log and filter out any unrelated hardware matrix information, and then eventually find the root causing pairs. For example, there are many aborted rungs that cause the cascade network timeout, but they are actually healthy. We need to filter out those noisy. This was very, very inefficient. Now let's take our approach. We use semi-online failure localization. Real time, we trace all the Nico last active network operation, and then when this stuckness happens, we run script to compare the last active network operations time point from all the ranks, and we can search the first pair that hits network error. It just takes a few seconds and we can figure out which two rungs are the root causing of the entire system deadlock. So for example, here we can see the actually two rungs of the FSP altogether hit a switch flip that caused the deadlock happen. Furthermore, this tool also allows us to generate human readable model level dependency of all the ongoing collective, allow developer to understand why the interdependent deadlock happen. So this is how we improved our finer debugging. Next, I want to hand over back to my partner Ashmitha for the final conclusion and the future work.
Thanks, Min. So to conclude this talk, some of the three conclusions that we can have from this talk is, firstly, network reliability is the foundation for large-scale training. A reliable network ensures that our distributed system can operate efficiently and effectively. Secondly, tool renovation for scalable solutions is important. As our models and clusters continue to grow in size and complexity, it becomes increasingly important to develop innovative tools that can keep up with this scale. We have observed that independent network metrics that tracks and maintains health of our networks are necessary, but they're not sufficient to debug large-scale performance issues. For this reason, we added instrumentation in our application stack to enable precise and low-cost observability and debuggability at real time. This kind of integrated approach provides a more comprehensive understanding of our system behavior, making it easier and more accurate to identify and diagnose issues, thus enabling a reliable network with significantly reduced operational effort. Some of the ongoing and the future work in this area. We are still continuing to build a more holistic and a fully online end-to-end automation system that can not only detect anomalies, but can automatically alert, mitigate, and recover from issues in real time while having minimal impact to our production jobs. Secondly, traditional hardware signals still give us a rich and precise signal regarding our machine health, but we are looking into ways to integrate these signals to gain a much more comprehensive understanding of our system health in a very lightweight and automated way. Lastly, with the detailed tracing that we have enabled with our custom library, we have a lot of information at our disposal, but we need to extract some core signals to inform future pathfinding efforts, such as identifying issues for optimizations or predicting any potential issues before they occur. Overall, the opportunities in this space to improve performance and failure debuggability are not just nice to haves, but fundamental to scale models to thousands of GPUs. Thank you.